Okay, now we move on the last topic for today, okay, on the brace cut design. So, however, this, as I mentioned you previously, it is discussed on the static problems or static load only. Okay? So it's very important when we want to construct, for example, for for a basement, okay, that we need to have a temporary structure, okay, before we construct for the basement. Okay. So deep excavation with vertical side require lateral support, okay, to prevent cave in of the earth and to protect the adjacent area against ground subsidence and lateral movement of the subsoil. So that is the important why we need to have a lateral support. Okay. So when excavation is shallow and ample space is available, the site of the excavation can be sloped at a safe angle to ensure stability. Okay. So let's say we have a very huge area and it's very shallow, so there will be no problem for us to construct for a slope. Okay. However, in a deep excavation, especially in built-up area, there may not be adequate space for providing safe slopes. Okay. Moreover, it becomes uneconomical to provide safe slope because of a large quantity of earth involved. Okay. So uh, that's why it's very important to have this kind of lateral support. Okay. Especially when we want to have a very deep excavation, okay, and we doesn't have any huge space to construct for a slope. Okay. So excavation which are laterally supported are braced. Okay. The vertical side of the excavation are supported by a sheeting and a bracing system. Okay. So this is an example of the bracing system, okay, that been used. Okay. So we need to cut in we need to excavate in the stages, okay, after we install the bracing systems. Okay. So this is on the um, side view, okay, or the front view. Okay. So for example, if we look on the three-dimensional view, okay, so let's say this is the area that we want to propose. Okay. So first, the installation of the uh, any sheet, uh, for example, sheet pile. Okay. First, we install the sheeting material first. Okay. So I will sheet like this one. Okay. Okay. So then we do the excavation. Okay. For example, we excavate a little bit here. Okay. And we excavate the whole area. Okay. Then we put what we call as a bracing system. Okay. So there should be what we call it as spacing between one bracing system with another bracing system. Okay. Okay, so this bracing system to protect from this lateral to provide a support. Okay, from this sheeting structure. Okay. Then excavate more. Okay, then produce what we call it provide the bracing. Okay, for the second layer. Okay. Then until to the required layer that we want to achieve. Okay. So the vertical side of the excavation are supported by sheeting and bracing system. Okay, it consists of relatively flexible sheeting placed against excavation wall, okay, the lateral thrust on the sheeting is resisted by the horizontal member in compression. Okay, so for every what we call for every brace, okay, so they provide what we call a strut. Okay. So bracing is provided and the excavation proceed and the face of the sheeting become exposed. So various type of the bracing system is adopted to make the excavation stable. Okay. Sheeting piling is used primarily as a bulkhead to hold or restrict the lateral movement behind it. Okay. So there will be several type of bracing system. Okay. So sheet pile is among the common type of method that used, okay, in this brace cut system. Okay. So a gravity retaining wall is a permanent structure used when excavation is a permanent. Okay. But when excavation is temporary, excavation for building or subway, the excavation is filled with a structure which then permanently retains surrounding soil or earth. Okay. So later on, uh, after the excavation is completed, okay, um, then we can remove this bracing system, okay, by and then replaced uh, by the by the permanent structure. Okay, if the temporary excavation is made in the sand, the wall of excavation must be supported during construction of the building by a system of bracing. Okay, so laying underground pipeline. Okay, so this is the type of construction that commonly use the this bracing system. Okay, the laying underground pipeline. Okay, construction of a bridge abutment, construction of a basement, uh, metro railway construction, construction of subway tunnel. Okay, so this is a part of the um, uh, structure that commonly use the base cut system. Okay, so unless if we are come up with uh, a method like let's say a tunnel, okay, or a trenchless method. Okay, so it is not required to use this base cut system. Okay, for example, if we build a trenchless pipeline, uh, so no need for us to have this base cut system. Okay. So type of brace cut system, we have a vertical timber sheeting, steel sheet pile, soldier beams, tie backs. Okay. So I just introduced the type of the system that commonly used. Okay. So this is example of the vertical timber sheeting. Okay. In this method, vertical timber sheeting consisting of the planks about 8 to 10 centimeter thick are driven around the boundary of the proposed excavation to a depth below the base of the excavations. Okay, so they call it as a plank. Okay? So they with 8 to 10 centimeter thick. Okay, so the soil between the sheeting is excavated. The sheeting is held in a place by system of the wheel. Okay, so this is the wheel. Okay, and strut. The wheel are the horizontal beam running parallel to excavation wall. Okay, so sorry, actually the wheel is let's okay this is the wheel. If we look on the three-dimensional, okay, to support the sheeting. Okay, the wheel are supported by horizontal strut. Okay, so this is the strut. Okay, which is uh to provide a support, okay, to the wheel. Okay. Another method, they use a raker if they doesn't want to use the strut. However, if the excavation is relatively wide, it's become economical to support the wheel by inclined strut known as a raker. Okay, for inclined strut, if for inclined strut to be successful, it is essential that the soil in the base of the excavation is strong enough to provide adequate reaction. Okay, so if it's very wide, so it's better to use the raker, but make sure that the soil at the platform is very strong enough. Okay, if the soil can temporarily support itself an excavation of limited depth without external support, the timber sheeting can be installed in the open or in partially completed excavation. Okay, if they feel that the soil is strong enough, so the soil, the surrounding soil is strong enough, so it doesn't require to use the strut or the rakers. Okay, just rely on the timber sheeting only. Okay, vertical timber sheeting are economical up to a depth of 4 to 6 meter. Okay, so that is the limitation of the timber sheeting method. Okay, so pile or sheeting driven in close contact to form a continuous interlocking wall which resists the lateral pressure of water of earth. In this method, the steel sheet pipe is driven around the boundary of the proposed excavation. A continuous line of pile is driven in advance of the excavation as the soil excavated from the excavation way and strut are placed. Okay. The wheels are made of the steel. The lateral thrust from the side is resisted by the horizontal member construct are placed across the excavation and which again the wheels. Okay, the strut may be of the steel, made of steel of or woods. So as the excavation progress, another set of wheel and strut is inserted. The process is continue till the excavation is complete. It is recommended that the sheet pile should be driven several meters below the bottom of the excavation to prevent local heat. Okay, if the width of the excavation is large, inclined bracing may be used. Okay, the same with the rakers that we have discussed. Okay, the upper strut is placed when the excavation is shallow and a little lateral of soil has occurred to change appreciably, appreciably the original state of stress. Okay. As excavation proceeds downward, the lateral part of the face is freely to yield inward before it could be restrained by the next strut. The inward yield of soil increase with the increase in the depth of excavation. Those problem is analog to a retaining wall tilting about its tops, the sheeting tilt about its tops. Okay. So that is the importance of using the otherwise it will start to tilt. Okay. So okay, this is the construction of the steel sheet pile. Okay, so this is the how we look on the top. Okay, so this is the sheet pile. Okay, so it has a wheel. Okay, so and then it put with the hard wood block and then it use the strut. Okay, so if we look on the continuous condition, so this wheel will be cross parallel with the sheet pile. Okay. Okay, so this is an example. Okay, we have here a wheel and strut. Okay, so this is the sheet pile. Okay. So another method they call as a soldier beams. Okay, which is the H pile. Okay. So this is the H pile. Okay. Are driven at a suitable spacing of 1.5 to 2 meter around the boundary of the proposed excavation. Okay. As the excavation proceeds, horizontal timber plank. Okay, so then they use another what we call it uh, sheeting. They use a timber. Okay, legging are placed between the soldier beams. So when excavation advances to suitable depth, width, and the strut are inserted, the legging is properly wedged between the pile and a pipe flinch or behind the back flinch. Okay, so they put between the within the H beam. So this is the plank. Okay, while this is the H beam with the what we got the distance 1.5 to 2.5. Okay, so a little bit very different with the continuous sheet pile. Okay, so another one is the tie back. In this method, no bracing, okay, in the form of strut or inclined racks is provided. Therefore, there is no hindrance to construction activity to be carried out inside the excavation area. So there will be no use of the strut. Okay? So they can have a proper, a very free area, okay, inside the, the excavation hole. So the tie back is a rod or cable connected to the sheeting or legging on the one side and anchored into the rock or soil, the soil of rock outside of the excavation area. Inclined hole are drilled in the soil or rock, then the tensile reinforced tendon is then inserted and the hole is concreted. An enlargement or bell is usually formed at the end of the hole. Okay, each tie back is generally pieced before the depth of excavation is increased further to cope with the increased tension. Okay, so then they use a concrete. Okay, then make sure that the concrete has been hardened. So then they will apply a tension force to make sure that this system, okay, contact well with the tie back system. Okay, so now we may learn on how to design, okay, for a brace cut system. Okay, but for this case we only focus on the what we call on the sheet pile system only. Okay, no discussion uh, will be made on the soldier beams or on the tie back. Okay, so for the timber sheeting, okay, the same system with the sheet pile. However, the difference is on the material only. Okay. So lateral earth pressure, rankine and column earth pressure cannot be used for the computation of the lateral earth pressure on sheeting, as those theory applicable to rigid retaining wall rotating about the base. Okay, so that is different. So we cannot use the rankine or column earth pressure. The sheeting and bracing system is somewhat flexible and rotation takes place at the top of the wall only. Sheeting are placed against the wall of the excavation when these are shallow. And the upper strut is placed when the excavation is shallow and the lateral yield of the soil has occurred. As the excavation proceeds downward, the lower part of the face is free, yield inward before the next strut is placed. Okay. So the inward yield of the soil increase with the increase of the depth of the excavation. Thus, the sheeting tilts about its tops. Okay, the method of the earth pressure of calculating has been developed by Terzaghi. Okay, so Terzaghi has proposed a method to calculate for the prescott system based on the observation of actual load in the strut in full-scale excavation in sand in Berlin and in soft clay in Chicago. So he observed this kind of movement, okay, on the sand and on the soft clay. Okay, pressure distribution against the sheeting has been approximated on the assumption that each strut support the sheeting area. The effect of the variance factor is not fully understood. However, the result of the field study can be used as a basis for developing earth pressure diagram required for the design of the pressing system. Okay, so this is based on the field study. So Terzaghi has come up with the formula based on the observation of the field study. Okay, the pressure diagram recommended for design represent an envelope which encompass the actual pressure distribution diagram obtained from the field test. Okay, these design pressure diagram are known as the apparent pressure diagram. So on the actual field test, they has observed the pressure distributions. Okay, so then they use this pressure distribution, okay, to come up with the design for this prescott system. Okay, the pressure diagram for prescott in dry or moist sand. The pressure diagram is uniform with a pressure PA equal. Okay, so this is the approach that we can use for the sand. Okay, 1.6 times PA over H or 0.65 unit weight times H times KA. Okay, so it's more easy to use the 0.65 since we are familiar with the KA. So the KA is refer to the Rankine equation with the tangent square times 45 minus 5 over 2. Okay. So the PA, the total normal active pressure on the wall of height H determined by the column theory. Okay. So the resultant active earth pressure diagram is 28% greater than the column active pressure for dense sand and 44% greater than the loose sand. Since the sheeting cannot resist, in general, the vertical shear force, the friction and addition of them are assumed to be zero. Okay. Sorry. Okay, so this is assumption made by the Terzaghi. Okay, so then Peck has come up with the pressure diagram. Okay, uh, uh, which is to be used for the sand, firm clay, and soft to medium clay. Okay. Um, so, for example, for the clay, okay, so we need to check for the stability number. Okay, if it is less than 4, okay, so we can call as a firm clay. So the diagram that we should use is refer to the diagram of B. Okay. So if greater than 4.0, okay, so the pressure envelope is shown in figure C. Okay. So we may use the formula, okay, or the equation or the diagram based on the formula or diagram in figure C. Okay. So the figure C is considered as the soft to medium clay, okay, while the figure B is referred to the firm clay. So in order to check for the stability, we need to know what is the unit weight of the soil, okay, times with the height of the uh, trench, and also divide with the cohesion value of the material. Okay. So that is for the pressure diagram for sand, firm clay, soft to medium clay. So now we may look on one example, okay, on a dense sand. Okay, so uh, I guess I will share with you another example on the clay. Okay, okay, after we discuss on the sand. Okay, okay. So for the sand, okay, so this is the diagram, the pressure diagram for the sand. Okay. So we may use this diagram to calculate uh, for the loads, and then propose for the uh, sheet pile, and also what will be the uh, value for the strut, and also for the wheels. So a long trench is excavated in a medium dense sand for the foundation of a multi-story building. Okay. The side of the trench are supported with sheet pile wall fixed in place by strut and wheel, as shown in figure 2017. Okay, so this is the diagrams of the sheet pile wall, wheels, and also strut. Okay. So the soil property are unit weight 18.5, C0, and phi equal to 38. Okay. So first determine the pressure distribution on the wall with respect to depth. Okay. Strut load. The strut are placed horizontally at a distance 4 meters center to center. Okay. So the bending moment for determine the pile wall section. Okay. So we need to determine what will be the bending moment. Okay. And the bending moment for determine the section of the wheel. Okay. So first we need to get the pressure distribution on the wall. Okay. So by using the sand diagrams, so we may calculate what will be the pressure acting on the wall. Okay. So 0.65 times gamma times H times Ka. Okay. So Ka we can get from this value. Okay. With the phi is equal to 38. So the value for the Pa is equal to 23. Okay. So that is the wall, that is the pressure acting on the wall. Okay. So the next is to calculate for the strut. Okay. Or it depends. Okay. If you want to start with the C, okay, then you continue with the B and D, so there will be no problems. Okay. So no need to 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 provide the solution, okay, based on the arrangement of the question. Okay. So okay, then okay, we start with the strut load. Okay, so based on this what we call as a distribution diagram. Okay, so we know where is the location of the strut. Okay, RA, RB, RC. Okay, due to the arrangement is symmetry. Okay, so we can solve first for the RA. and RB1. Okay, then we may use the same value later on because the arrangement or the spacing is same. Okay. Okay. So the reaction of the end of the strut A, B, C are represented by RA, RB, and RC. Okay. So the reaction RA, okay, takes moment about B. Okay. So this is the RA. Okay. Well, this is the RB, or they separate into B1. Okay. So then we may we may calculate based on the moment, okay, which is the RA, okay, towards the B times with 3, okay. So the RA uh, is equal to 4, okay, times 23, okay. 23 is obtained from the pressure, which is 23, okay, uh, times 4 over 2, okay. Okay, sorry, this is the RA, okay, and sorry, let me draw. Okay, so for example, this is B, okay, so this is RA, okay, and this is the pressure, which is 23, okay, so that's why 23 times 4, 4 is the distance between D to B, okay, then the moment arm is 4 over 2, okay, equal to RA. So this is the RA, okay. Then it should be timed with 3 because the distance is 3, okay. So equal to the moment from the force of the soil, okay. So then later on RA is equal to 60.33. Okay, so that is for the RA. Okay. So then to gain for the RB, okay, so 23 times 4 should be minus with the 61.33. So that is for the RB1. Okay. Due to the symmetry of the load distribution, okay, which is RB1, RB2, okay, is equal to 30.67, okay, and definitely the RA and RC is 61.33, okay. So now the strut load are 4 meter, which is the L, okay. So for the strut A, PA is equal to 60.33 times 4, which is equivalent to 245 kilonewton, okay. Then for the strut B, okay, because previously we differentiate between RB1 and RB2, okay, actually it is the same. RB1 plus RB2 is equal to the RB, okay. So times 4, so it also produces the same value because it is a symmetry in terms of the equation. Okay, then the last one, due to the PA is similar with the the PC is similar with the PA, so the value of the strut is equal to 245. Okay, so that is for the strut load value. Okay, so then for the moment of the pile wall, okay, to determine the moment at different point, it is necessary to draw a diagram showing the shear force distributions. Okay, So from the moment we may come up with this diagram, shear force distributions. Okay. So this shear force distribution will be used, okay, uh, to determine the what we call as the moment of the pile section. Okay. So consider dB1 and B2E of the wall. Okay, the distribution of the shear wall force are shown in, okay, in this diagrams. Okay. The moment at different point may be determined as follow. Okay, so for example, the MA is the half times 1 times 23. Okay, 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 this is the MA. Okay, and then for the MC, okay, MC same, okay, is the half time 1 times 23. Okay, however, for the MM, okay, is the half time 1.33 times 30.67. Okay, which is this one. Okay, okay, to get the value 1.67 and 1.33, so we need to use what we call as the triangular similar triangular methods. Okay, so that is for the MM, and it is same with the MM. Okay, based on the value, okay, so the maximum moment M max should be used is equal to 20.4. Okay, so that is the moment of the pile wall section, which is equal to 20.4. Okay, so then a suitable section of pile can be determined as per standard practice. Okay, so what should we do next? You need to refer for any catalog from the manufacturer. Okay, and then find what is the specification of any ship pile which is equivalent to 20.4 in terms of the maximum moment, okay, of the pile wall section. Okay, so that is for the C. Okay, and then for the D, okay, is the maximum moment for wheel. Okay, so the bending moment equation for wheel, okay, which is the M max is equal to RL square over 8. Okay, where the R is the maximum strut load that we already calculated previously. Okay, and L is the spacing of the strut, which is 4 meter. Okay, so the maximum moment for the wheel by using this equation, okay, is equal to 490 kilonewton meter. Okay, so in that case, we need to determine, we need to look on the catalog. Okay, what will be the specification for the strut to be used in order to cater for the 490 maximum moment. So not the strut, for the wheel, for the wheel. Okay, okay, so that is for the sandy soil. Okay. Okay. Okay, actually I have shared with you this PDF on the clay material. Okay, so this is example of the breeze cut, okay, on the clay. Okay, so um, almost similar with this, sorry, almost similar with the one that we have discussed for the sand, but the difference definitely on the distribution diagrams. Okay, So for this case, okay, actually first we need to determine what is the stability number, okay, because if it is less than 4, then we can propose to use this what we call as the firm clay uh, pressure diagrams. Is greater than 4, then we need to change to the soft to medium clay distribution diagrams. Okay. So the brief example is shown above. Determine the earth pressure, strut location at A, B, C, section modulus of sheet pile, section modulus of the wheels at B. Okay. So strut are placed 3 meter center to center. Okay. So that is the question. Okay. Okay. So we have here earth pressure. Okay. So unit weight 18, C 35. Then the height is equal to 7 meter. Okay, 1.75 plus 3.5 plus 1.75. So then later on we check for the stability. Okay, so it missing here H. Actually gamma H over C. So it is less than 4. So in that case, we choose this what we call as distribution diagram. Okay. Pressure distribution diagram. Okay. So the pressure diagram should be used is C. Okay. Then 0.3 times 18 times 7. Okay. So that is the equation that should be used. Okay. To determine the maximum value. Okay. For the delta A. Okay. Which is 0.3 times unit weight times the height. Okay. So that is the maximum. Okay. Then the strut load. Okay. So the same procedure with the previous one. Okay, where we need to calculate for the moment. Okay. So for this example, okay, this is the moment diagram. Okay. It's sorry, this is the reaction. Okay. Diagram. Okay. Then this is the shear force diagrams. Okay. So we can look on this uh, diagram to 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 determine what will be the strut load. Okay. Okay. So then for the strut at the PA, the value is equal to 162.02, while for the PB, okay, is have a very high value, okay, due to the maximum of the delta A is equal to 37.8 is occur at the strut B. Okay. Okay. Then the PC is similar with the PA, okay, which is equal to 162.06. Okay. So then to calculate for the section modulus of the pile, okay, from the reaction diagram, okay, we need to come up from we need to come up from the moment diagram, we need to come up with the shear force diagram, okay. So from there, uh, okay, this is how we calculate for the distance between X. Okay, so by using what we call as a triangular law, if I'm not mistaken. Okay, to get the value for the X. Okay, so for example, 42.5. Okay, RR 42.5, and then X is equal. So RR is equal to R A B1 over 30.7, 42.5 2/37. Okay. Let me check first. Okay. Uh, 2.5. 2.5 x equal to 3.2 x. Um, Actually, I obtained 1.276, okay, for the X, okay, 42 point. But in this example, they obtain 42, sorry, 1.169, okay, okay, R times RAB1 42.2, 45.2 over 7.8 to 1.1. Okay, so they just divide the 42.5 over 37.8. So they obtain 1.169. Okay, the magnitude of the moment at A. Okay, so they just uh, later on they uh, uh, the magnitude at A. Okay, this position. Okay, 37.8 over 1.75 times 1 times 1/3, okay, time 1/2. So they obtain 3.6. So that is the moment at A. Okay, the magnitude of the moment at E, okay, okay, at E, so they obtain 27.03. Okay, so due to the symmetrical magnitude of A, E equal to CF, here's the maximum. So then they come up with the maximum value of 27.03. Okay, therefore the shear modulus. Okay, so either you want to calculate, you can get the, you want to calculate for the shear modulus, section modulus. So the maximum divide with the, this is the, what we call is uh, the strength of the material, okay, and this is the value that you can gain later on, okay. Okay, that is for the section modulus, okay. So for, sorry, that is for the not the, sorry, the section model of the sheet pile, okay. Then for the section model of the wheel, okay, I guess similar with what we have discussed in the sand, okay. So by using this formula, then we come up with the maximum shear modulus of the wheel, and maximum modulus of the wheel, okay, for the B. Then calculate for the section modulus to get section modulus of the wheel, okay. Okay, so that is for the clay material for the firm clay problems. Okay. So this is not from my example, this is from Prof. Ramli example. So if you are not very convenient with this example, so you for example for especially on the calculation of this x, I'm also not familiar how they gain the x. Okay? So you can look on the sand problems, and then uh, from there you can apply the same uh, concept for the clay, especially on the shear force diagram. Okay, so that's all for the brace guide. Uh, okay, so